Okay, so we have an applied electrodynamics practice final exam, graduate level. I'm going to go through this quickly. Some of the intermediate steps aren't there, but here is the basic overview of it. Number one, a grounded conducting sphere of radius A is centered at the origin. A point charge Q is located on the z-axis at position z equals d, where d is greater than A. Part A, using the method of images, determine the electrostatic potential outside the sphere. So, electrostatic boundary value problem. So we have the grounded conducting sphere. Point charge Q is at z equals d, with d is greater than A. For a grounded sphere, use an image charge. Q prime is negative Q times A over D. Place that z prime equals B equals A squared over D. And for a potential outside the sphere, for R is greater than or equal to A, we just have this V of R equation, right, which is rather canonical. Some of the equations I'm not going to read. I'm just going to point to them because I realized it's right there. You could pause the video. You could see the variables. So for V of R theta, by the way, this is just a 1 over 4 pi epsilon naught times this whole quantity. Okay. And over here is r squared plus a to the 4th over d squared minus 2r times a squared over d. Okay. And this satisfies v of a comma theta equals 0. For part B, find the induced surface charge density on the sphere. So for the induced surface charge density, that's going to be this. The sigma equals that negative E naught partial dV dr, R equals A. And when we differentiate, we get the following. And that's it. That is our induced charged surface density of the sphere after we differentiate. I omitted some steps, but we just want to get you through this. So you have a reference for practice problems. So the sign is negative as expected for a positive external charge. Part C, determine the total induced charge on the sphere. The grounded sphere has a total induced charge equal to the image charge. So the Q sub IND, that's negative Q times A over D. And for part D, calculate the force acting on the point charge. So here, force on the charge, the force is the Coulomb force between Q and its image charge, Q prime, and their separation is this D minus B, given here. And then that F sub Z equals this. We're going to substitute Q prime. That's going to equal negative QA over D. And the force is attractive towards the sphere. Here is the force. Okay. All right. So, moving along to number 2. Start here. Sorry about that. So, whoops. Sorry. Some humor. Okay, so here we go. Number 2, a localized charge distribution has density given here. Show that the total charge vanishes. Okay, so here, multiple expansion and energy type problem. We have rho of r theta equals rho naught e to the negative r over a times cosine theta. Total charge, we're going to use this. Q equals the integral rho d cubed r. And then using d cubed r is the following. R squared sine theta dr d theta d phi. We're going to say Q equals rho naught from 0 to infinity r squared e to the negative r over a dr times from 0 to pi cosine sine d theta, and then 0 to 2 pi d d phi. So we have a multivariable integral. We break it up in the components, and then the nice thing here is from 0 to pi, the cosine sine d theta component, that equals 0 when we take the definite integral of that. So therefore, our Q is going to wind up equal to 0. Okay, so part B, compute the electric dipole moment vector So dipole moment is this, equal to this integrated, that we're integrating r prime p of r prime d to third r prime. And then here, by symmetry, only p sub z is non-zero. Okay, so p sub z equals this integral r cosine theta rho of r comma theta d cubed r. And so p sub z equals rho naught from 0 to infinity r cubed e to the negative r over a dr, 0 to pi cosine squared sine theta d theta, and then 0 to 2 pi integrated d phi. Now we have this. Sorry if I didn't say rho and I said p instead. Sometimes I read too fast. 0 to infinity r cubed e to the negative r over a dr. That equals 6a to the fourth. This component, 0 to pi cosine squared sine theta d theta gives you 2/3. And then this component for 0 to 2 pi d phi gives you 2 pi. Multiply them together and we wind up with 8 pi rho naught a to the fourth. And so our electric dipole moment vector is going to equal 8 pi rho naught a to the fourth in z hat. Okay. Letter C, find the leading order far field electrostatic potential. Okay, so since the leading term is dipolar, well, we have this V of R theta. That's the 1 over 4 pi epsilon naught times the dot product of P and R hat over R squared. So V of R theta is going to be this 1 over 4 pi epsilon naught times 8 pi times, I'll just say this whole quantity, that's a rho naught there, a to the fourth cosine theta over R squared, and reducing that gives you the following for V of R theta. Okay, and for part D, determine the electrostatic energy stored in the dipole field outside a sphere of radius capital R much greater than lowercase a. So here for dipole, this is what we're given for E sub R and E sub theta. And the energy here for U, that's going to be this integral, indefinite integral R to infinity, and using this entire expression here. We're going to wind up with, when we do the computation, and with P is 8 pi rho naught a to the fourth, we're going to wind up with U sub outside is this. Okay, and pretty much moving along. Yeah, we're good. We're good. What looks like we're okay with letter D. Okay, so moving forward, so two forms of that. That's A, B, C, D. Moving along to number 3. Okay, so number 3, let's see what we have here. Let's see if this holds up. Okay, an infinitely long cylindrical conductor of radius A carries, so this is of radius A, carries current density. And here's our current density. Okay, this is J of R. Part A, determine the total current carried by the conductor. So this is a magnetostatics and vector potential problem. Cylindrical current distribution, J of R equals this as given. Here's our total current, I equals the integral of J sub Z dA. So I is 2 pi J naught from 0 to A. We have 1 minus R squared over A squared R dr. Integrating that from 0 to A, computing, we get I equals pi J naught A squared over 2. Part B, using Ampere's law, compute the magnetic field everywhere. So here the magnetic field by symmetry, this magnetic field is B sub phi R of R and phi hat, and Ampere's law gives that B sub phi of 2 pi R equals mu naught I enclosed, and for R is less than A, that I enclosed is 2 pi J naught, integrating from 0 to R of that 1 minus, now R prime squared over a squared r prime dr prime. Okay, so when we compute this, we're going to wind up with this for our I enclosed, this expression here, and this quantity here. And then thus we could say that that b sub phi of r is going to equal all of this. Okay. And now, b sub phi of r is going to wind up equaling mu naught j naught a squared over 4r, where r is greater than a, given the following. Okay, so moving along to C, construct a vector potential A consistent with Coulomb gauge. So vector potential, choose this A is equal to a sub z of r z hat, and then b sub phi is equal to negative d dr of that a times negative d az of dr. For r is greater than 0, this d a sub z dr equals negative u naught j naught times r squared, r over 2 rather, minus r cubed over 4a squared. And we're going to integrate that, performing the integration a sub z r. Since it's indefinite integral, we're going to need a c, since it wasn't bounded by limits of integration yet in this problem. So a sub z of r equals c minus u naught j naught times this quantity r squared over 4 minus r to the fourth over 16a squared. So we choose a sub z of a equals 0, and then we get our c equals 3 mu naught j naught a squared over 16. So a sub z of r equals mu naught j naught times all of this, 3a squared over 16 minus r squared over 4 plus r to the fourth over 16a squared, where r is less than a. And for r is greater than a, we get this dA sub z dr equals negative mu naught j naught a squared over 4r. Thus, we wind up with a sub z of r as c minus mu naught j naught a squared over 4 ln r. Using a sub z of a, we get equals 0. And then we wind up with a sub z of r, okay, equals mu naught j naught a squared over 4 ln a over r, where r is greater than a. Okay, so it's consistent with Coulomb gauge. And the verification here, with that cross product del cross a equals b, the verification, well, for a equals a sub z of r z hat, del cross a equals negative d a sub z dr phi hat, and differentiating the expressions above gives exactly the fields in part B. Okay, gives the fields in part B. So del cross A winds up equal to B. Okay, so moving along here, that was number 3. We're ready for number 4. Okay, so number 4, let's see if that holds. Okay, number 4, electromagnetic induction and energy flow. A circular conducting loop of radius A and resistance R lies in the XY plane. A spatially uniform magnetic field is applied. Right here, B of t equals B naught e to the negative t over tau z hat. Part A, find the induced EMF in the loop. Okay, so induction in a circular loop. Okay, we're given that, induced EMF. Here's the flux. The flux is B of t pi a squared. And then Faraday's law gives the following, negative ddt of the flux. So since dB dt equals B naught over t e to the negative t over tau, we get this. Okay, so that's the induced EMF in the loop. Okay, so that's our, and that's not epsilon, that's script E. All the time I call it epsilon. Go back to script E. If I'm talking too fast, I see it too fast. Same thing with omega and W, iota and L. I often have that issue. Even calling lowercase e sometimes with the electrons Euler's number by accident. My brain skips a lot. I get brain freezes and whatnot. I am Just sometimes, who knows? Okay, letter B, current in direction. Determine the induced current and its direction. I equals, okay, we have the EMF over R, so thus that I of t is going to equal this quantity here. By the way, sorry about that, that's a tau in the denominator here, and that e to the negative t over tau. Now we could say the following: because the external positive z hat magnetic field is decreasing, the induced current creates a positive z hat field. So viewed from positive z hat, the current is counterclockwise. So that's interesting there. Conceptual portion of B. Part C. Calculate the total energy dissipated in the resistor. So here's the energy dissipated integral. U equals 0 to infinity I squared R dt. And we calculate this indefinite integral, performing all the computation. We're going to get tau over 2. And that's at the end, we're going to get for our energy dissipated in the resistor, it's going to be U equals pi squared a to the 4th B naught squared over 2 R tau. Okay, and part D, discuss how energy conservation is reflected through the Poynting vector. Okay, so here the changing magnetic field creates a circulating electric field. That electric field drives the current, and electromagnetic energy flows into the wire through the Poynting vector. And the energy lost by the field equals the joule heat dissipated in the resistor. So that's like textbook canonical stuff, important. That's A, B, C, D for number 4. Ready for number 5. Okay, again, I'm going through this quickly because you could pause the video. You could try these problems. This is just extra practice. Part 5, number 5, a plane electromagnetic wave propagates through a conductor of conductivity sigma. Permittivity and permeability. Starting from Maxwell's equations, derive the wave function for the electric field. So this is canonical, super important wave equation for the electric field here. Electromagnetic waves in conducting media type problem. So wave equation, if we use Maxwell's famous equations, okay, that here, what we're going to do is we're going to take the curl of the Faraday's law, okay, and we're going to get negative d dt of quantity del cross B, and using the dot product of del cross E equals 0, and we have these del cross E, that equals negative del squared E. Now here, that negative del squared E, that equals negative mu sigma dE dt partial minus mu, and then this permittivity, and then the second partial with respect to time here of E. And so we get this for our del squared E. We get this wonderful, very useful formula. Okay, so that's our wave function for the electric field. Super, super important and very elegant where it comes from. Part B, assume harmonic time dependence e to the negative I omega t and derive the complex propagation constant. So assume E equals E naught, E to the I k z minus omega t. So del squared E is that's equal to negative k squared E, and partial derivative here d dt equals negative I omega E. Second partial with respect to time of V is negative omega squared E. Now we're going to substitute. Negative k squared is negative I omega mu sigma minus omega squared mu permittivity. Okay, so from here, k squared is going to equal the following. Mu permittivity omega squared plus I mu sigma times omega. And here's our value of k. K is W times the square root of mu permittivity times the quantity 1 plus I times sigma over permittivity omega. Okay, so that's for part B, propagation constant K. Part C, determine the skin depth in the good conductor limit. So we need to take into consideration what a good conductor means. So here in a good conductor, our sigma is much, much greater than our permittivity times omega. And then our K squared here, our propagation constant squared is approximately I mu sigma omega. And going back to complex numbers, square root of I is 1 plus I over square root of 2. So we could rewrite this and isolate K. K is about 1 plus I times the square root of mu sigma omega over 2. And then the attenuation constant is alpha equals the square root of mu sigma omega over 2. So from there, the skin depth is delta, and I apologize for my horribly drawn delta. Delta equals 1 over alpha equals that's square root of 2 over mu sigma omega. Okay, and discuss the phase relationship between electric and magnetic fields in this regime. So here, phase relation. In a good conductor, the electric and magnetic fields are not exactly in phase. They're not. The magnetic field lags or leads depending on convention, but the phase shift is approximately 45 degrees. The wave also decays exponentially as e to the negative z over delta. Okay, so that takes care of number 5. So moving along to number 6. Okay. Okay, number 6 here. Radiation from oscillating dipole. An electric dipole moment oscillates harmonically. Here's what we're given. Okay, derive the far zone electric and magnetic radiation fields. So the radiation from an oscillating dipole. Okay, oscillating electric dipole. Here's what we were given for our equation. For far zone fields in the radiation zone, we have this E theta equals this mu naught, this whole thing here. Okay, this should be very familiar. This is canonical, and then our B phi equals this canonical. And we could say the fields are transverse and proportional to 1 over r. So this is more of a textbook thing. Very important, though. Very, very important. And I shouldn't have said derive. I should have said demonstrate for letter A, technically. For part B, here we have our average of S. Okay, so here, compute the time average Poynting vector. So here, what we want to do. So average of S, that is this equation, and where E naught equals this. So automatically, if we go ahead and we perform the operations, our average of S equals this whole thing. So this is the time average Poynting vector. And technically, this is very textbook-like for letter B as well. Canonical. Determine the angular distribution of radiated power. This is also important. Angular distribution. The radiated power per solid angle is this dp d omega derivative here equals r squared average of S. So dp d omega equals this whole thing when we calculate it. And a note here, the radiation is strongest perpendicular to the dipole axis and 0 along the dipole axis. So that's where the radiation is stronger. Sorry about writing that small. And for part D, find the total radiated power. Okay, total radiated power is going to be equal to this integral dp d omega. And we're going to use the following integral of sine squared theta d omega. Sorry for that horribly drawn omega. That's going to come out to 8 pi over 3. And we're going to get this for the total radiated power. Here's going to be our quantity. And for part E, explain why no monopole electromagnetic radiation exists. So why no monopole radiation in this situation? So electromagnetic monopole radiation will require time-varying total electric charge, but charge is conserved. dq dt, that derivative is equal to 0, change in q with respect to time. So therefore, the lowest allowed electric radiation multiple here is dipole radiation. Okay, hopefully I didn't mispronounce too much there. I know I'm talking fast, whatnot. Okay, so from here, number 7. Number 7 we could do rather quickly. They're just asking us this question: is I of z comma t equals I naught del of z e to the negative t squared over tau squared idealized y or y naught. And this is just a short answer here, just potential causality type problem. So the current given here is idealized and not physically complete by itself because charge conservation would require an associated charge density. So that was kind of like a trick question. I don't know, textbook type question, but you might have known it immediately. Okay, that's it for number 7. Moving along to number 8. Okay, so I'm going to go through this quickly. Number 8, consider the electromagnetic field tensor given. Construct it explicitly in terms of E and B. So covariant electrodynamics for this field tensor using the convention with metric signature plus minus minus minus. Here's what it would be. Okay, so the electromagnetic field tensor would be this. Okay, all right. And this is a bit canonical in a lot of textbook stuff. These are for part B. I mean, this to show how Maxwell's equation can be written compactly using tensor notation. Here they are. For Maxwell's equations, here's the inhomogeneous equations become this, and the homogeneous equations become this, or equivalently this. Okay, and this is the dual tensor. This is textbook notes type stuff for A and B. For part C, identify the Lorentz invariance constructed from the electromagnetic field tensor given here. So Lorentz invariance, the two main invariants are E dot B and E squared minus C squared B squared, up to conventional constant factors. Okay, so that's part C. And part D, determine whether there exists an inertial frame in which the magnetic field vanishes when magnitude of E is greater than C times magnitude of B, where E is perpendicular to B. Explain. Okay, so frame where B prime equals 0, given this, what we're given here, we have E squared minus C squared B squared is greater than 0, and E dot B is 0. So therefore, there exists a frame where the yield is purely electric, where your B prime equals 0. The required boost is E cross B with speed. Since E is greater than CB, the speed is less than C. And this is if your V, we take into consideration our V here equals C squared E cross B over E squared. So that's for part D there, and let's now move along to number 9. Okay, so number 9. Okay, so particle of charge Q and rest mass M moves relativistically in cross fields. E equals E naught X hat, B equals B naught Z hat. Write the relativistic Lorentz force equation. Okay, so this is canonical. Relativistic motion in electromagnetic fields, the relativistic Lorentz force. Here we go for dBdt, Q times quantity E plus V cross B, where we have here our two equations given for Lorentz force. I mean, this is textbook stuff. Okay, so sorry, throat's bothering me a little bit. My apologies. For part B, determine the drift velocity here, given this inequality. Well, the drift velocity for cross fields with this E naught is less than C B naught. Okay, here the drift velocity is V sub D is E cross B over B squared, and we could basically say that E cross B equals E naught B naught times the quantity X hat crossed Z hat, and then we have, well, that equals negative E naught B naught Y hat, which thus we have the following for our drift velocity there. Part C, find the inertial frame in which the electric field vanishes. Okay, so if E naught here is less than C B naught, there exists a frame moving at V equals E cross B over B squared. Relative to the lab, so E prime equals 0. And for this problem, our V, that equals that negative E naught over B naught Y hat. Okay, so think about what we have here and there. And part D, discuss the physical interpretation of this transformed frame. So we could say this. In this frame, the particle sees only a magnetic field, so its motion is helical or circular rather than being accelerated by an electric field. The lab frame drift comes from transforming this simpler magnetic-only motion back to the original frame. So that's number 9. And now we go to number 10. This is the last one of the practice exam problems. So number 10 here, a rectangular waveguide has dimensions given. Okay, derive the cutoff frequency for TE modes. So waveguides and dispersion. Okay, so transverse electric modes, cutoff frequency. So for TE modes, that K sub Z squared, that equals M pi over A squared plus N pi over B squared. The cutoff angular frequency is W sub C equals CK sub C. So that WC Mn equals C pi square root of M over A squared plus N over B squared. And that F sub C Mn equals C over 2 square root M over A squared plus N over B squared. And for TE modes, M and N are not both 0. Okay. Part B, determine the dominant propagating mode. So here, the dominant mode, since A is greater than B, the lowest cutoff frequency is for M equals 0, N equals 0. Thus, the dominant mode is TE 10 with cutoff frequency F sub C 10, C equals rather C over 2A. Okay. Sorry. Part C, find expressions for phase and group velocities. So our propagation constant, our beta here, is the square root of omega squared over C squared minus K sub C squared. So the phase velocity here, omega over beta. And our group velocity is going to be d omega over d beta. And if we want to use omega squared equals C squared times the quantity beta squared plus K sub C squared, if we differentiate that, 2 omega times d omega d beta, that equals 2c squared beta. So our group velocity comes out to that c squared beta over omega. And here we could, for part D, we could rely on the previous equations to help us show that the product of phase and group velocity satisfies this. This V sub P, V sub G equals C squared. Well, V sub P, V sub G, if we just substitute from what we had before, we have omega over B times this C squared beta over omega. These cancel out, and the omegas and the betas cancel out. We get C squared. And part E, explain why the phase velocity may exceed C without violating relativity. Okay, so for part E here, since our phase velocity equals omega over beta equals omega over beta greater than C, the phase velocity can exceed C. But this does not violate relativity because information and energy propagate at the group velocity, which satisfies V sub G is less than C for propagating waveguide modes. Okay, so that's all, and I apologize if I miscommunicated anything or talked too fast. Hopefully this could help for extra practice problems for applied electrodynamics. And thank you very much and have a great day.